Hello, everyone, and welcome to another virtual lesson. My name is Michael Faribault, and I teach AP Chemistry at Albemarle High School in Charlottesville, Virginia. Now, today I'm going to be going over the answers to the questions that were given in yesterday's lesson. So if you're watching this video and you have not had the opportunity to take a look at the sample questions from yesterday's video, I strongly encourage you to watch yesterday's video, or at least click on the link in the video description that will take you to the questions, sample questions 1 and 2 from Wednesday. I'm going to go ahead and talk about the correct answers as well as the answers that we received that were perhaps highlighting some misconceptions. We had a lot of great student responses. We had students that wrote their answer. I would say I prefer slightly the appearance of the writing on the right. On the left, it was a little difficult to read, so make sure when you snap that picture, just double check that you've got good contrast. Remember to use dark pencil, dark, blue or black ink. Make sure that it's easy to read. And of course, we also had students that typed and submitted their responses. All right, so I'm going to go ahead and begin with sample question number 1. Common additives to drinking water include elemental chlorine, chloride ions, and phosphate ions. Recently, reports of elevated lead levels in drinking water have been reported in cities with pipes that contain lead. And we are talking about the reaction between lead and chlorine in part A. And they mentioned that some of the lead atoms oxidize, losing 2 electrons each. So we're going to need to see some lead ions. And it also mentions that aqueous chloride ions form. So we're going to need to see some chloride ions. So we are starting with lead and aqueous chlorine, Cl2. And then we're going to finish with these products, the lead ions and the chloride ions. Now, if this was my final answer, I would not receive full credit because I have not balanced the equation. So I'd have to add a 2 right there. Okay, and then that would be a fine way to express it. You don't necessarily need to show the phases of matter. So for example, some students did put in S for solid and AQ for aqueous, but remember that symbols for phases of matter are not required. All right, let's take a look at some sample student answers. All right, we have some handwritten answers that look correct. And again, you can see some have included phases of matter and some have not. That's fine. We have some typed answers. Again, notice that we're not worried here about superscripts and subscripts. That's fine. So the readers will understand what you mean. So don't worry that you have to have fancy symbols there. This person uses a caret symbol. Again, that's totally fine. So just you can see a variety of different acceptable answers. Now, here are some answers that indicate some misconceptions or some concerns. So here we have a charge of +4 on the lead, but they specifically said that lead loses 2 electrons. Again, the problem here is that the charge on the lead is +2 in the reactants, but we were told that we're going to start with lead as in just elemental lead, lead solid. This one is looking really close to being correct, but they now have a charge of -2 on a single chloride ion. And again, down here, we don't have any lead at all. So they have eliminated the lead completely. So these are some concerns and some misconceptions. Now, a certain number of students did report this as their answer. If you look ahead to the next part of the question where solubility product constants are going to be given, I could see why a student might have been concerned about writing the products of the reaction as lead and chloride, because they might have said, well, if lead chloride is rather insoluble in water, then it has produced a precipitate. So I can't give you a definitive answer on this one. I can tell you that the official scoring guidelines that I have indicated that the product should be the lead ions and the chloride ions, but again, perhaps this would be a discussion that could be had among readers and the leadership, but I'm just going to tell you that I was looking for lead ions and chloride ions in my scoring guidelines on this one. Okay. Now, speaking of KSP, we have not only lead chloride, we also have lead phosphate. So notice that we have coefficients here, and these coefficients will be featured as exponents in the KSP expression. So we have the concentration of lead raised to the third power times the concentration of phosphate raised to the second power. That is the expression for KSP. Let's take a look at some handwritten answers. All right, these all look good. And let's take a look at some typed answers. Again, just to remind you that you don't have to necessarily use fancy superscripts and subscripts. So this is still acceptable. Okay, so notice that we have a 2+, and then we have the little caret symbol. Again, that's fine. Okay, so these are acceptable in terms of typing and having it all be on one line. Now, here are some concerns. Here's some misconceptions. I have some students who had written products over reactants. Remember that we do not include a pure liquid or a pure solid in the equilibrium expression. So that's why there is not going to be a denominator in this case. So again, just a concern to watch out for. With a KSP, there's only going to be the aqueous ions, but not the solid reactant in your expression. And then some other, just some careless errors. It should be raised to the second power, not the third power. And we do not need extra numbers inside the brackets. This might indicate some kind of extra coefficient. So again, that would be a potential concern for your symbols. This person wrote the expression and wrote the KSP, but never wrote the value of the KSP, but never actually wrote the concentration of lead and the concentration of phosphate. So this is an incomplete answer. All right, let's go ahead and take a look at part C, which has to do with the KSP. Calculate the molar solubility of the lead phosphate. So for every X moles of lead phosphate that dissolves, we get 3x for the number of moles of lead ions, and we get 2x for the number of moles of phosphate ions. So we're solving for X, which is the solubility of the compound as a whole. So therefore, inside the brackets, inside the parentheses, we have to have 3x and 2x. And let's take a look at some math here. We have 3 times 3, which is 9, times 3, which is 27. And then, of course, we have 2 squared, which is 4. So we should have 27 times x to the third power and 4 times x squared. Now, 27 times 4 . 7 times 4 is 28. Carry the 2. 2 times 4 is 8, plus 2 is 10. 27 times 4 is 108. So that means that we have 108 times x to the fifth equals 1.08 times 10 to the negative 53. That was given in the table. So we can divide both sides by 108. Now, of course, 108 is also 1.08 times 10 to the second power. That makes this part of the math pretty easy. So we have 10 to the negative 53 divided by 10 to the second power. When you subtract, you should get 10 to the negative 55. So that means that on the left side of the equation, we have x to the fifth power. And on the right side of the equation, we have 1 times 10 to the negative 55. Now we can raise both sides of the equation to the 1/5 power. So we can solve for x. And when you do a power to a power, that means that we have negative 55 times 1/5. That should be negative 11. So our answer to this question is 1 times 10 to the negative 11. That is the solubility in moles per liter of lead phosphate. Let's take a look at some handwritten answers. All right, so there we go. You can see they're showing their work. and indicating that the value is 1 times 10 to the negative 11 moles per liter. Let's take a look at some typed responses. Again, you might use superscripts, but if you don't have the ability to do that, this is fine. Take a look at this answer. We can see that it says 1.08 times the 10, caret symbol, negative 53. They've got all of their math there. Looks good. All right, let's talk about some concerns or misconceptions. This person does beautiful work and gets the correct answer. However, I think there's some confusion about solubility and the KSP value. So they have put a box around the value, which is kind of similar to the KSP without the 0.08 part. So they've expressed this as their final answer when in fact the answer was 1 times 10 to the negative 11. So be careful that you understand the difference between the solubility of a compound in moles per liter and the numerical value of the KSP, the solubility product constant. All right, watch out here. We're doing 3 squared. Okay, 3 squared is 27. So this person made the mental math error that 3 to the 3rd power is 9. Again, same kind of thing here. We see a 36 because they did 9 times 4 instead of 27 times 4. This person did have a problem setting it up because they included a denominator. So their math is off. Again, there should not be any chemical in the denominator for a KSP expression. So they plugged in another number here. We saw this, I saw this occasionally. We have no 3x and 2x. So now we just have x to the 5th. So that's going to give you a different numerical answer. That's the same thing kind of here. We have, they're showing x and x as opposed to 3x and 2x. So therefore they have x to the 5th instead of 108 times x to the 5th. I think what this person did in terms of math is, this is all looking good, but I believe what they did is they raised both sides to the 1/5 power. And that caused the equation to be incorrect because they just kind of ignored the 108 and they raised this number to the 1/5 power and then they divided by 108. That's just a math error. This person starts off looking good with 3x and 2x, but somehow changes that to x. So again, watch out for little calculation errors or computation errors like that. All right, moving on to part D. Using the table of KSP values above, explain why the addition of phosphate is more effective at reducing lead concentrations in drinking water than chloride. Now, what does that mean? Reducing lead concentrations. Well, that means decreasing the concentration of lead, which would be a shift toward the left, toward the solid. So you could talk about the difference in the magnitude of the KSP values, because there's definitely a difference there. You also could talk about the stoichiometry. For every 2 moles of phosphate that react with lead to make a precipitate, you can remove 3 moles of lead from solution if you move in this direction from right to left. But for every 2 moles of chloride ions, you can only remove 1 mole of lead. So you could have talked about stoichiometry or you could have talked about KSP. I'll show you both. So one possible answer was, given that the KSP for lead phosphate is so much smaller than the KSP for lead chloride, the molar solubility of lead phosphate is much lower. So therefore, the phosphate ions will be much more likely to form a solid precipitate when they interact with these aqueous lead ions. So again, comparing the KSP. Or you could have said that the ratio between chloride and lead is 2 to 1, whereas the ratio between phosphate and lead is 2 to 3. So if I have an equal molar amount of phosphate and chloride, it would precipitate more lead ions. The phosphate would precipitate more lead than the chloride would. All right, let's take a look at some sample student answers. I like this answer because it actually mentions both. Didn't have to do that, but it talks about everything that I just mentioned. It says the table shows that the KSP value for lead phosphate is much less than that of lead chloride, meaning that lead phosphate is less soluble than lead chloride. So adding phosphate to drinking water will cause the equilibrium to shift left, producing more lead phosphate and using up more of the concentration of lead. This is more effective than adding chloride because 1 lead ion reacts with every 2 chloride ions, while 3 lead ions react with every 2 phosphate ions. So adding phosphate would result in the depletion of more lead ions from solution than adding chloride. Great answer. All right, these answers, both typed and handwritten, are focusing on the smaller size of the KSP. The KSP is much lower, smaller KSP value. Its molar solubility is much lower because the KSP is so low. Again, KSP value is smaller. Okay. And then here we have some answers focusing on the stoichiometry and the mole ratio. So we're looking at the fact that for every 1 mole of phosphate, we reduce the lead by 3/2. Whereas for every 1 mole of chloride, we reduce the amount of lead by 1/2. So again, focusing on the ratio. Here this person says when 2 moles of chloride is added, only 1 mole of lead is removed, whereas when 2 moles of phosphate are added, 3 moles. Okay, so it looks great. All right, let's take a look at some concerns and some misconceptions. The addition of phosphate is more effective than at reducing lead because phosphate is insoluble. Okay, so that's not correct. It's not the phosphate itself, but rather the entire lead phosphate compound you want to be talking about. This person says because phosphate has a greater oxidation number. That's not what's going on here. This person says that phosphate is more basic and has to do with the acid-base reaction. So it's not about acid-base chemistry, it's about precipitation. All right. Now we have part E, where we have given a concentration of lead that's already in the sample of water. And now we have a concentration of phosphate. So we can go ahead and calculate what is called Q. So Q is the opportunity to plug in into the KSP expression, the reaction quotient. You plug in the numbers you have right now. And we decide if Q is greater than or less than the KSP. So if Q is greater than the KSP, then we're definitely going to have a precipitate because we're going to shift the equilibrium toward the formation of the solid product. If for some reason Q is less than KSP, then you would not have a precipitate. So we'll take a look at that. All right, plugging in the numbers. And again, don't forget we have the expression here for KSP, just using the numbers we have. 1.0 times 10 to the negative 9. Now that is raised to the 3rd power. So that part's going to give us a power to a power, means you multiply the exponents. So we have 10 to the negative 27. Over here, we have 3 times 10 to the negative 5th squared. So 3 times 3 is 9. And then 10 to the negative 5th squared would be 10 to the negative 10. So multiplying all these together, we get 9 times 10 to the negative 37. Okay, so that's a little bit of mental math. 9 times 10 to the negative 37. Comparing that to the KSP, we can see that even though 9 times 10 to the negative 37 is a rather small number on its own, it is larger than the KSP. So this means we are going to have a shift in the equilibrium toward the formation of a solid precipitate, and that would cause the concentration of the lead in solution to decrease. All right, here we have some sample student answers, both written and typed. Q is greater than KSP. Here they do the math. Therefore, the concentration of lead would decrease. Okay, here they do the math. They say this is greater than KSP. Concentration of lead would decrease. Okay, there's the math. Q is greater than KSP, than the K, so the lead decreases. Again, this is typed out and this still works. Again, no fancy superscripts or subscripts. We got it. 9 times 10 to the negative 37. Therefore, the concentration of lead will decrease. Okay, now let's take a look at some misconceptions or some concerns. All right. This is the great value that we're looking at, except they said the concentration of lead will increase. So they had the right idea for Q versus K, but they expressed the incorrect answer about what's going to happen to the concentration of lead. All right, this says lead would decrease. And they say Q is greater than KSP. So the problem here is they didn't actually show us the calculation. So in this answer, we don't know that Q is greater than KSP because we don't have calculated number to compare it to. This person says the KSP will always be constant, but they don't compare Q with K. So they say that lead would decrease, but we're not getting a significant understanding of Q versus K. All right, higher concentrations of lead are found in pipes carrying hot water than in pipes carrying cold water. Is this observation consistent with a negative enthalpy of dissolution? So if I have solid in an equilibrium with aqueous ions, and we're saying that in hot water, so there's a higher temperature, this concentration is higher. So that means that there must have been a shift toward the aqueous ions as a result of a higher temperature. Typically, when you raise the temperature, the reaction equilibrium will shift in the endothermic direction. So therefore, this observation would be consistent with an endothermic enthalpy of dissolution. Now they're saying negative enthalpy, so I would disagree with this statement because a negative enthalpy means exothermic, and we are talking about endothermic shifting toward the aqueous ions. So I'm going to say no, that it's not consistent. And I said a negative enthalpy change would make the dissolution exothermic. At higher temperatures, an exothermic dissolution would actually shift to the left. Because if heat is essentially a product and you're adding more heat by raising the temperature, you would shift it in the endothermic direction. That would be from right to left if it were an exothermic process. So this observation is consistent with a positive enthalpy or an endothermic process. Let's take a look at some student answers. All right, this person says no, that's good. This observation is consistent with a positive enthalpy because the lead concentration is increasing at a higher temperature. Looks good. Talking about delta H being positive. No, this is consistent with a positive delta H because heat would go in on the reactant side, which would produce more products if the reactant was in hot water. Again, talking about Le Chatelier's principle and shifting toward the right. This person says, no, it does not. A negative delta H is exothermic, but if heat is increased, the reaction would shift toward the left and more precipitate would form. So these are all good. All right, here are some concerns and misconceptions. This person says, yes, this is consistent with a negative enthalpy. So they are agreeing with it. And they're saying that temperature can affect the equilibrium and a higher temperature would push the reaction toward the products. So again, they're confused about what endothermic and exothermic mean with respect to dissolution. This person says, yes, it is consistent with a negative enthalpy because if the reaction releases energy, there'll be a higher concentration of lead in the warmer water. That is incorrect. This person says if delta H of solution was negative, the dissolution would be negative, releasing heat. Therefore, yes, talking about a higher temperature and the formation of products. So again, they're not quite understanding that endothermic, raising the temperature, would shift it toward the formation of the aqueous ions. All right, let's move on to the next part of the question. Here we have a double bond and 3 single bonds. And here we have 4 single bonds. We are given the bond length for a single bond and a double bond. And so we'll be talking about this information in both parts G and H. Using diagram 1, the student claims that the bond angles are all 90 degrees. Well, just because I can draw water like this, does not mean that the bond angle in water is 180 degrees, just because I have drawn the atoms in a straight line. So just because you are looking at what seems like a 90-degree angle in a Lewis structure, this doesn't tell us, according to VS EPR theory, what that looks like. So I would disagree with the bond angle of 90, and the geometry of the ion should be tetrahedral. It's sp3 hybridization. So we're looking at a bond angle of 109.5. And so many students agreed with this particular situation. well, they disagree with the 90, but they understand what's going on, I should say. So this person says, I disagree. The geometry is tetrahedral, so it should be 109. The student's claims are false. It's tetrahedral. It should be 109.5, not 90. I disagree. It's tetrahedral. The bond angles are 109.5. This person says SP3, about 109. Okay. This person says, I agree, it's tetrahedral, and therefore the bond angles in tetrahedral are 90 degrees. Again, so be careful on that. That is incorrect. So just because you can draw a molecule with a 90-degree angle does not tell you what the actual geometry is. All right, now on to the bond length. Let's talk a little bit about resonance because that might have come up. And I'm not sure if you had been thinking about resonance, but I'm going to go ahead and talk about that a little bit. Okay, here are two classic examples of resonance that are mentioned in chemistry textbooks and in chemistry classes. So you can see I'm showing you a bond length for a single bond between oxygen of 148 and a double bond of, that should be 121. Sorry about that decimal point, 121. Okay. Now, just from this data, you can tell that a double bond is shorter than a single bond, as you should know. Now, because there are two equivalent resonance structures, the actual bond length in ozone, O3, is somewhat in between 121 and 148. This is benzene, C6H6, and we have two resonance structures. So the shorter bond length is 134 picometers. The longer bond length is 154. And because these are all equivalent and are kind of in between, the bond length is 140. Now let's go back to our question. We have two numbers, 163 and 150. That number is really close to 163. So therefore, in my opinion, based on the fact that a double bond is much shorter than a single bond, and that we are told that all four PO bonds in phosphate have a bond length of 162.5, I'm going to prefer this diagram. Makes it difficult to argue for this diagram because we have one double bond and three single bonds. And if you do the math, if you take the average, so multiply this by 3, multiply this by 1, and then add them together, you're going to get an average that's around 160, 159 point something. So I think that the fact that 162.5 is really close to 163, it would suggest that structure 2, in which all bonds have the same length and showing consistent single bonds, and since the bond length in phosphate is 162.5, it is reasonable to assume that double bonds are not present in the structure, only single bonds which have the same bond length. Let's take a look at some student answers. Diagram 2 is consistent with this finding, as all of the PO bonds in diagram 2 are single bonds which are of equal length, while in diagram 1 has one double and three single bonds, which would cause different bond lengths. Now, this person is not talking about resonance at all, just simply the two structures compared side by side. Another person says, diagram 1 contains a PO bond that is double. That means that the bond length will be shorter than the single bonded PO. So again, they're not talking about resonance, but simply you have uneven bond lengths, whereas in diagram 2, all of the bonds are single bonds and are the same length. Now, this person does do the math for averaging 3 singles and a double. This also, same kind of calculation. And so they say that the observed 162.5 is more likely for diagram 2, where all the bonds are single at 163. So they were considering resonance and considering that this average bond length is too short compared to the observed 162.5. Now, just another caution here. Remember to read the question carefully and answer the question. So we were supposed to choose either diagram 1 or diagram 2, and this person says no, but I'm not sure what they're disagreeing with. It wasn't a claim, it was simply which diagram 1 or diagram 2. So you have to choose one. So be careful that when you finish your answer, go back and reread that question one more time and make sure that you actually answered what is being asked. All right, here we have a particle diagram and we have hydrogen bonding. So we're looking at hydrogen bonding. Sometimes there's hydrogen bonding occurring between two water molecules. And then sometimes we have hydrogen bonding where the oxygen of the phosphate is connected to the hydrogen of a water molecule. And so we're supposed to consider what the problem is, identify the letter corresponding to an incorrect hydrogen bonding interaction, and how the diagram should be changed. So some students talked about which was incorrect, but they never indicated how the diagram should be changed. So since oxygen is more electronegative than phosphorus, it is likely that in the phosphate ion, the phosphate would have a partial positive charge. Therefore, the partial positive of hydrogen in a water molecule would not be connected to the partial positive charge in the phosphate. So here we have the mistake based on charges. The student should rotate the water molecule and show an attraction between the oxygen in water and the phosphorus in phosphate. They're saying that the partial negative of water should have been oriented toward that partial positive. Okay, that was one approach. Another approach is to focus on the fact that you could have moved the hydrogen in the water molecule so it was oriented toward one of the oxygens, so that phosphorus does not participate in hydrogen bonding. Instead, it's nitrogen, oxygen, and fluorine. So the student should move the dashed line to one of the exterior oxygen atoms, which would participate in hydrogen bonding. Okay, let's take a look at some student answers. They definitely said that A was the incorrect bonding interaction. That's good. And then how they should fix it. The dashed line needs to be moved so that the H connects to another O. The H and the H2O should be attracted to the O of the phosphate. The H in letter A should instead be bonded to the O directly adjacent to the phosphorus. Hydrogen bonds only connect a hydrogen from one compound to either an N, O, or an F. To make it correct, the student should instead bond the H to an O on phosphate instead of the P. Okay, looks good. This person said A is incorrect. And except for this diagram, I was concerned that they didn't quite talk about what the correction should be. But sure enough, you can see that they have redrawn the diagram to show that the hydrogen on the water molecule is connected to the oxygen on the phosphate. So it looks good. This person's a little bit confused. It says that the correction is that the line should be changed to a straight line instead of a dotted line. Okay, that's not the change that we're talking about. This person says letter A is incorrect, talks about why it's incorrect, but they never actually suggested what the change should be. They're just talking about why A is incorrect. This person is indicating that only C is correct and everything else is incorrect because, in their opinion, hydrogen bonding should only take place between water molecules. It says because phosphate is nonpolar, it does not have any hydrogen bonding. So remember that an electronegative oxygen, even in a substance like phosphate, which is a polyatomic ion, can still reach out to form a hydrogen bonding interaction with the hydrogen on a water molecule. And again, this is a concern, and we have this concern on the AP exam every year. Confusion between intermolecular forces and intramolecular attractive forces. So when they say that hydrogen bonds are a covalent type of bond, that causes concern. Okay, so again, we're looking at an intermolecular or interparticle force. All right, moving on to the next part. We have phosphorus, which is 1s2, 2s2, 2p6, 3s2, and then 3p3. So according to the scale, it's only going up to that spot right there. Oxygen, we have 1s2, 2s2, and 2p4. The student notices that the rightmost peak of the O is taller than the rightmost peak of phosphorus. Now, the student claims that this is because oxygen has fewer occupied electron shells, which means that the valence electrons are closer to the nucleus and experience greater attraction. So we have to disagree with this claim. We're focusing on P3 versus P4. So the height of the peak has to do with the number of electrons. It's not about the attraction, it's about how many electrons are in that particular orbital at that particular peak. So disagree. The vertical height of a peak in a photoelectron spectrum corresponds to the number of electrons, not the strength or attraction to the nucleus. It is true that oxygen has a smaller radius than phosphorus. Now, in terms of the binding energy, you can see that the binding energy, if you look closely along the x-axis, it is a little bit higher. But that's a result of the peak being shifted to the left for oxygen not being taller. So we're going to disagree and talk about number of electrons. All right, the student is not correct. The peak heights have to do with the number of electrons, 4 versus 3. Looks good. I disagree. The height of each peak is related to how many electrons occupy that sublevel, comparing P4 and P3 configurations. All right, this person disagrees, but they say because oxygen has less electrons in the 2s orbital than phosphorus. Okay, so that's not true. And then we had several people that agreed. I agree because oxygen is smaller. I agree because of the binding energy. I agree because phosphorus has a different nuclear charge. So again, it is about the number of electrons. So you were supposed to disagree with that claim. All right, let's move on to sample question number 2. Methanoic acid, HCOOH aqueous, is a monoprotic acid that can be synthesized by the reaction between CO and NH3. So we can see that there are the reactants, CO and NH3, in the presence of hydronium ions. A proposed mechanism for the reaction consists of 3 elementary steps as shown below. Write the chemical formula for a species that behaves as a catalyst. So we have a catalyst, which is the CH3OH that's added in step 1 and then produced as a product in step 2. That is a catalyst. So lots of people got this right. Again, don't worry about things like capitalization or subscripts. These are all fine. CH3OH is what we're looking for. Some people were confused, so they had thought that NH3 or CO or HCO2CH3, which is actually intermediate. Again, these are not the catalysts. Part B, according to the proposed mechanism, and again, we're going to focus on the rate determining step here. So our actual rate coming from the rate determining step would be including these chemicals. It's okay to include a catalyst in the rate determining step if it is part of the slow, in the rate law. It's okay to include a catalyst in the rate law if it's part of the rate determining step. According to the proposed mechanism, if additional NH3 is added to the reaction mixture, will the rate of the overall reaction increase, decrease, or remain the same? NH3 is not in the rate law. It's not in the rate determining step. So therefore, this should have no effect. The rate will remain the same. The rate law for this reaction is the same as that for the rate determining step in step 1, which includes the concentration of CH3OH and the concentration of CO. Since NH3 does not appear in the overall rate law, increasing its concentration should not affect the rate. Let's take a look at some student answers. This person says the overall rate remains the same. The rate reaction for the overall rate is the rate reaction for the slow step, the rate determining step, and NH3 is not involved in the slow step. Looks good. Okay, NH3 is not in the rate determining step. This all looks great. All right, here's some misconceptions and concerns. The overall rate is increased by the addition of NH3 because steps 2 and 3 are faster than step 1, or that somehow adding NH3 would quicken the fast steps. So some confusion about what exactly the rate determining step has on the overall rate law. Okay, so just because a chemical is in the fast step does not mean adding more of it's going to make it faster. This person says NH3 is a reactant and therefore should be a factor. But again, they're not understanding about the rate determining step. This person says that it should increase because there are more faster, stronger collisions. Again, all of these are misconceptions. All right, the next part, part C, is the student's diagram, which shows going from reactants to products. Is it consistent with the enthalpy? Now, the enthalpy is negative. The enthalpy change is negative, so this is an exothermic process. So the answer is no. Because the overall reaction is exothermic, as indicated by the negative delta H, the products should be lower in potential energy than the reactants. As the reactants convert to lower potential energy products, energy is released. So we have to disagree and say no. No, delta H is negative. The arrow should be going from reactants to products, as in going down, not up. No, because the overall reaction is exothermic and loses energy, whereas the diagram implies it's endothermic. Okay, these are all good answers. No, based on the negative enthalpy, the reaction is exothermic, and that's not reflected in the diagram, which shows a higher amount of potential energy for products than reactants. All right, here's some misconceptions. This person says yes, because all the reactants and products are in the correct place. This person says yes, since the reactants of the combined steps are at the bottom and the products are included. So again, these are misconceptions. All right, next part, we're going to talk about the types of intermolecular forces, and that includes London dispersion forces, dipole-dipole forces, because these molecules are both polar. They are definitely asymmetrical, in which the bond dipoles are not going to cancel out. And they have hydrogen bonding attractions. They experience hydrogen bonding attractions. Again, they experience hydrogen bonding attractions with other molecules because they contain a hydrogen directly bonded to an oxygen. So all three of these IMFs would be experienced. LDFs, dispersion forces, dipole-dipole, and hydrogen bonding. Okay, so we have a nice list. You can say LDF for short, that's fine. LDF, dipole-dipole, hydrogen bonding. You can write them out. You can abbreviate. Looks good. Now, if you said London dispersion forces and hydrogen bonding, I would accept that as well. Both have a special form of the dipole-dipole force known as hydrogen bonding. Okay, sounds good. But they never did mention LDFs. So if you're going to mention all of the intermolecular forces, you have to be complete. So just to be on the safe side, it'd be a good idea in this case to say London dispersion forces, dipole-dipole forces, and hydrogen bonding. Again, be a discussion at the reading whether or not dipole-dipole forces be required, because again, many teachers explain that hydrogen bonding is a special kind of dipole-dipole force, but in this answer, not mentioning LDFs is incomplete. This person says that CH3OH has dipole-dipole and London forces, but they never actually said. They left off the part about hydrogen bonding. And then a little more cause for concern down here because they're including things like ionic bonds. Okay, so again, some misconceptions and incomplete answers on this page. All right, when an equimolar mixture of the two compounds is heated to 50 degrees Celsius in distillation, the vapor phase contains a higher mole fraction of CH3OH molecules. So that means that it's essentially saying it's easier for CH3OH to go from a liquid to a gas. The fact that there is a higher mole fraction of molecules in the vapor phase, the gas phase. We've got to talk about the strength of the intermolecular forces. And this molecule has a larger electron cloud because there are two oxygens as opposed to only one oxygen on the right. So larger electron cloud means you could talk about London dispersion forces. Also, with two oxygens, you have two opportunities to form hydrogen bonding interactions. So you could have talked about that there is an extra spot for hydrogen bonding. that would indicate that there should be stronger intermolecular attractive forces, which the HCOOH has a little bit more than the CH3OH. Okay, so you could have said CH3OH must have weaker intermolecular forces than HCOOH. HCOOH has greater dispersion forces because it has a larger, more polarizable electron cloud due to the extra oxygen atom. Or the polarity of the CO bond in the HCOOH molecule provides another region of partial negative charge that can attract the slightly positive H atom in a neighboring molecule. So again, extra opportunities for forming hydrogen bonding interactions. Okay, here are some student answers. This person talks about the extra oxygen and the polarizability and the stronger intermolecular forces related to that LDF, London dispersion force. This person says 2 oxygen atoms, so therefore we're looking for an extra amount of spots for hydrogen bonding. So having only 1 oxygen reduces the number of hydrogen bonds. All right, here's some concerns and misconceptions. There is hydrogen bonding in HCOOH, while CH3OH does not have hydrogen bonding. Okay, so that's a problem. And then this person says, it shows that the IMFs of CH3OH are weaker and easier to break, and mentions dipole-dipole forces that are somehow present in one molecule but not in the other, as if somehow only one molecule has dipole-dipole forces. So again, some misconceptions there. All right, now I want to make a very important point about this next part because of something I saw on one of the students' responses. Okay, we're looking at a titration experiment. In Unit 4, we have things like stoichiometry, reactions, titration, acid-base reactions. All of this is fair game for a question like this, okay? We're given a balanced chemical equation. We're talking about a titration experiment. Now, there is other stuff about acid-base titration and weak acids and weak bases that is mentioned in Unit 8. But you should definitely be able to do the information in Unit 4 and therefore answer a question like you saw in the sample. Okay, this was my concern. My teacher told me not to answer parts F through H because it deals with acids and bases. While Units 8 and 9 are not going to be tested on the 2020 exam for AP Chemistry, there definitely is acid-base chemistry and information about the technique known as titration that will be featured. No, you are not going to see a pH curve like this, but you should definitely be familiar with titration as a technique and stoichiometry as it applies to this situation. So here is a molarity calculation, which is based on the volume of sodium hydroxide that was used in this experiment to titrate a 20 milliliter sample of the methanoic acid. So we are given the volume in trial 1 and the molarity of the sodium hydroxide. Now 0.300 capital M, that means 0.300 moles of sodium hydroxide per 1 liter. I have written this conversion factor as 1,000 milliliters so I can get my milliliters to cancel out. As you can see in the stoichiometry, there is a 1-to-1 mole ratio between the acid and the base. And that number, 16.67 times 0.3 divided by 1,000 is equal to 0.005. That's not the final answer. That is the moles of acid present in a 20 milliliter sample. So the molarity would be moles divided by liters. So not 20, but 0.02 liters. 0.005 divided by 0.02 is 0.25. So correct answer, 0.25. That's what we're looking for. Okay, so showing some work to get a molarity of the acid of 0.25. Here are some student answers. All right. Again, they're not showing superscripts and subscripts, but I can definitely see what they're doing, and they got the answer of 0.25. So again, you are welcome to type your answer. You don't have to show fancy handwritten dimensional analysis, so typing is fine. This says molarity times volume equals molarity times volume. That is true when you have a 1-to-1 mole ratio between the acid and the base. So that calculation works. Okay, this person did the math and got 0.25. Okay, here are some more correct answers. M times V equals M times V, 0.25. These all look good. All right. Reminder, if you're going to type your answers, you have to show work. So in part F, all I see is the correct answer, but I don't see any supporting work. So be careful that you don't fall into that trap. Some other misconceptions would be the person that did this calculation was using the final burette readings from trials 2 and 1 instead of using the volume of the titrant in trial 1. And then this person down here, they used the final burette reading instead of the volume of titrant. So that's a mistake from reading the table. This person has a calculation, but involves moles divided by volume. It should be divided by the total volume of the acid. So they've got this combined total. They combined those two volumes together. That's incorrect. And then this person somehow converted milliliters to grams and then went from grams to moles. So again, that's incorrect. We have 20 milliliters. We do not have 20 grams of the acid. All right, so can we read a burette? Well, we're going to read from top to bottom. And that math is going to give us an estimate. We're going to estimate that the bottom of the meniscus falls somewhere between 18.1 and 18.2, and we read this out to the 100th place. So I'm looking for 18.1 something minus the initial burette reading. So a volume with 2 decimal places, 17.06, that's just what I did. You could be off by a little bit, and that's fine. So 17.06 is what I said, but you could have said 17.03, 17.07. Again, all of these have 2 decimal places and are based on the reading of the burette. All right, some misconceptions. Rounding off to the 10th place instead of the 100th place. Calling the volume 18.0, we know that the volume is definitely below 18 on the burette. So 18.0 is not a good reading of the burette. And this person read it from bottom to top and said it was 19.8. So again, those are some misconceptions. All right, now in this last part of the question, it says the student calculates, okay, so we have a certain value of the HCOOH. We have a certain number of moles of this chemical. The student calculates a value of the concentration of the acid that is significantly higher than the value for the other 2 trials. And the student claims that the reason for the higher calculated concentration is that water remained in the flask, which means that more NaOH was added. Now, extra water is not going to make a difference here because the reaction is based on the acid and the base. It's based on the moles of the acid and the moles of base. Having a little bit of water is not going to make a difference because we are focusing on the moles of acid. So I disagree. Having extra water in the flask does not change the moles of acid contained, only the volume. The number of moles of sodium hydroxide needed to neutralize the acid will be the same regardless if the flask is wet or dry. So this does not explain why trial 2 required a greater volume of sodium hydroxide. All right, I disagree because the calculation is based on moles. I disagree because the number of moles remains the same. I disagree because the amount of sodium hydroxide remains the same to neutralize, even if additional water is added, because the same amount of moles is present. Okay, so those are all good answers. This person says, I disagree because water doesn't affect the volume, but they don't actually talk about the moles of acid. So simply saying it doesn't affect the volume, I think I need a little bit more than that. I disagree because water is a neutral compound and would not affect the amount of base. Again, I would talk about how the fact that the moles of HCOH are the same. I disagree because because more water would actually make the concentration lower and not higher. So again, they're not quite understanding the concept there. I agree with the student claim because if more sodium hydroxide was added, they actually flipped it. Okay, so they're talking about a scenario in which more sodium hydroxide was added and they don't talk about the water in the flask. So they've kind of changed the question. So again, reminder to carefully read the question and answer the question that is being asked. All right, so that wraps up our lesson. I hope that those answers and explanations were helpful. Go to cb.org/AP2020 Get Ready, and reminder to take these 5 steps to get ready for your exam. And I'll put the important links on my final slide. All right, well, thank you everyone for watching. Tune in tomorrow and we'll do some final tips and tricks and strategies for your success on the AP Chemistry exam. Thanks for watching.